Okay. Okay. Yeah. Oh, somebody says that they are doing worksheets. Very good. Very good. Yes. From discussions. Okay. For those of you who are listening on YouTube, eventually, so we are just starting a lecture. Let me share the slides. So I will actually use the slides this time, mostly, and then sometimes the board. Okay, so hi everyone. So today we will do solving linear recurrence relations. We'll do homogeneous ones, and they are covered in section 8.15. 8.16 extends it to non-homogeneous ones. We will skip it in lecture. I ask you to do this, the 16 one, and it will is on. You have to read the stuff and do participation activities. So this makes it a little bit, tries to enforce that you actually follow and understand. But we will not have it on the test. Okay. So let's jump through it. So we had this recursive definition of sequences, right? We call them recurrence relations. Oh, and Isabel says that there is even fewer people. Yeah, so maybe 20 was an optimistic thing. Annie told me just 20 was yesterday or 2 days ago. All right. Even more, I encourage you to attend. Okay, so we have this recursive definition of sequences, right? We start with some base point, and then, you have a recurrence relation that defines the nth element as a sum function of the previous element in the sequence, right? So it's a recursion that goes in a loop and defines G1 in terms of G0, G2 in terms of G1, etc. So a closed form solution for this recurrence relation. So this defines a unique sequence. So there has to be only one, it's a unique definition of a sequence. There's only one sequence that satisfies this. So there is some way of computing the nth element, right? It's well defined. It's some function of n. That function exists. But what is it? Well, it happens to be this function. So an nth element is this function of n. That's called a closed form solution because the nth element of the sequence is defined as in terms of some function whose only argument is n. There is no other elements of G sequence in here, right? So you can, if all you're interested in is like, what's the value of the sequence at point 1000, you can compute it without computing all the previous elements. Okay. Now, using induction, we can verify that such formula is correct, right? So that's what we did. We last week and the week before, you were given some formula, or on the test 1, and a recurrence relation, and I asked you use induction to prove that this formula is correct. But how do you come up with these formulas? So this is what we're talking about now. Okay, how to solve the recurrence relations? Let's first categorize recurrence relations into subgroups, because in life what we're going to talk about today is solving them for a specific restricted class. This class is called linear and homogeneous recurrence relations. Let's look first what linear means. So here is the recurrence relation. The nth element is defined as some function of n minus first and n minus second, and also n itself. This is linear in that if you look at as Gn as a function of the previous elements, it is a linear function. The previous elements, what is a linear function? F of x1, x2, x3, etc., whatever arguments is linear if the f is defined as some constant times x1 plus some constant times x2 plus some constant x3, etc. Right? So in one dimension, when you have only x, this is a line. It's ax plus b. Yes, that's the linear relation. In a three dimension, you have two, x and y. The value for z is ax plus by plus some offset. Right? That's a line in space. So these are linear functions. And here is a non-linear function. This recurrence relation is non-linear. It takes this term and squares it. This is non-linear term because it takes previous elements and multiplies them. This we also consider non-linear because it's not a constant in front of this term. Okay, so the only one that we call a linear recurrence relation is this one. Now, we call a recurrence relation homogeneous if it doesn't have this extra term. In other words, it is just a linear function of the previous elements, of some number of previous elements, here 2. There could be only 1, or there could be 3 or 4, right? But it's a linear function of previous elements, like here, and nothing else. We call these extra, if such extra terms appear, we call them the non-homogeneous terms. And basically today, and in section 15, we only talk about solving these. Section 8.16 talks about like how do you take what we learned today and use it to solve recurrence relations that have non-homogeneous terms. But we'll not get there today, so you are on your own with that extension. Okay. And yes, you can have a non-homogeneous, non-linear. If this term was dropped or these terms were dropped, these would be non-homogeneous. Non-linear but homogeneous equations. But we will not. Neither section is going to tell you how to solve an equation of this type. Although maybe you can look at Wikipedia and other sources and generalize what you learn here to these cases as well. Okay, let's look at some, how to tell linear from nonlinear, homogeneous from non-homogeneous. So how about this guy? Gn is square root times Gn minus 1 plus 3 times Gn minus 2 plus 1. Is it linear? Is it homogeneous? So it is linear, but not homogeneous, exactly, right? It's linear because these are some constants multiplied by these terms. So as a function of previous terms, it's a linear function. But it is non-homogeneous because it has this free term at the end. Okay. So how about this list? So this guys, let's look at linearity first. It's linear because 3 and 4 are constants. What about the next guy? Linear, 3, and what's the constant here? Is 1/5, right? It's 1/5. Here, the constant is 3. Here, there are two constants. Log 2 is a constant times this guy and plus 5 times this. Here, it's non-linear because this is not a constant. And here is non-linear because it's a multiplication of two terms, of two previous terms, right? Now, is it homogeneous? No, because it's a free term. This guy is so homogeneous. There is no free term. This is a non-homogeneous term. This is homogeneous. It's a constant times Gn minus 2, constant. Oh, by the way, I guess I skipped that over. Look, I only take n minus second and n minus 7th. So what happened with the previous one? So is it really the case of a homogeneous recurrence relation? Because what about the constant in front of g n minus 1 and all the other terms? Well, they are implicitly here. The constants are 0. And so it is a function of previous 7 elements with the 0 as constant for the other terms. And it is linear. It is homogeneous because it doesn't have extra term. And these are homogeneous, but we sort of don't care because they're not linear. Oh, no. Oh, non-constant coefficients. No, I don't think these are considered linear functions. Okay, let's take it offline. I'm replying to someone a question on chat. Sorry. Okay. So let's look at solving these homogeneous and linear and homogeneous recurrence relations. So these relations always have this form, right? It's a previous d nth element of the sequence is defined as some linear function of previous d elements. So this is the first previous one, the second, the one before, and so how many of elements I have here? D elements, D previous elements, right, of the sequence. And I take them and I apply a linear function to them because C1, C2, CD are all constants. And that's how I compute. So, for example, Fibonacci, right? It is the C1 and C2 are 1, and that's it. D is 2 in the case of Fibonacci, right? Or a geometric sequence, D is just 1, and C1 is a constant of rate of growth of the geometric sequence. Okay, the number of previous terms that you take is called the degree of the recurrence relation, right? So a geometric sequence is degree 1, Fibonacci is degree 2, and here we have degree D. And if some of them previous ones are constants, that's still a 0. That's still a degree D. So this relation here is a degree 7 relation, recurrence relation. Okay. So what do we do to solve this? So here is a complete magic out of the blue sky. Recurrence relation of this form, every solution to them has such form. It's x to the n for some base x. And all we need to do is to find what base that is. Okay. And okay, so how do we find this base? So this is a kind of a guess. I mean, it's not a guess. We can also prove that that these are the only solutions. But in fact, you can prove this after this lecture. But but for this second, just assume that these are indeed the solutions. So let's say you have a recurrence relation like this. How can you find the base in this equation? Just stick it in. So replace fn by x to the n. If this is the general equation for the function, then this element is x to n minus 1. And this is x to n minus 2, right? So if this is a closed form solution for sequence f for every n, therefore it works for all of these guys. And if this is true, then so must this be. And now from this, you are almost home, because look, it's an equation that has a lot of powers of x on all sides. But let's eliminate common powers of x. This is a nth power, this is n minus first, and this is n minus second. There is a x to the n minus 2 in all these terms, because x n minus 2 is here explicitly. X n minus 1 is x n minus 2 times x, and x to the n is x n minus 2 times x squared. So when I divide by x to the n minus second, this vanishes, so I just got a 6. X to the n minus first minus n minus 2, if you work this out, this is just 1. So the only exponent remaining here is 1. And the exponent remaining here is 2. I mean, you can check, you can cross multiply now by this term. And if you multiply this, you are getting this, obviously. If you multiply 5x by this, you're getting x to first plus n minus second, meaning n minus 1. And this is x to 2 added, right? Because if you multiply x to something times x to something else, you're adding these exponents. So they come out to n. Okay, and now you just solve this quadratic equation, and that's your x. Okay. Now, so I'm just copying from the previous slide. This solution, this recurrence relation, gave me this equation for what base x must be in general formula for solutions to this, which is always of the form x to the n. This equation is called a characteristic equation for a recurrence relation. And you can get to this equation following the method on the previous slide. It is always a degree D equation, right? Because if you have an x to the n term and x to the n minus 1 and x to the n minus 2, x to the n minus d, when you remove the x to the minus n minus d term, there is what kind of x to what remain. The highest power is going to be on this side, and it's going to be x to the d. Okay, which is x to 2 in this case, because the degree of this equation is 2. And now we just have to solve this quadratic equation. Okay, so you have to recall how to solve quadratic equations. There is a general formula for doing them, right? You compute the so-called delta, and then you take the you have a formula for the roots. Another thing is just guess. Replace this by x to x minus something times x minus something else, and toy with these two. This something is actually a root, and just toy with them so that their sum is 5 and their product is 6. In this case, this equation satisfies, right? Because x minus 2 times x minus 3 is indeed this thing. So you can check that 2 squared 4 minus 20 minus 10, sorry, plus 6 is a 0, and also 9 minus 15 plus 6 is a 0. Okay, so there's two solutions here corresponding to the two roots. So when I said that every solution has this form, well, it turns out that there's actually two solutions like this. Fn can be equal to 2 to the n, and Fn can be also equal to 3 to the n. And both of them satisfy this recurrence relation. Okay, so both exponents of exponential with base 2 and exponential with base 3 satisfies this recurrence relation. How can it be that a single recurrence relation defines can be solved by two different functions? Well, the answer is it depends on the initial conditions, because the recurrence relation does not define a sequence yet. Recurrence relation together with base cases, these two things define a sequence. So you know without looking at base cases that the recurrence relation, the solutions are just these two. And now you have to look at which of these two really work, right? Because a recurrence relation defines a unique sequence. Yes, it does, together with base cases. And okay, so we'll see that in a second. But how can there be two correct answers? Well, the answer is even more general than this, more complex, quote unquote, than this. Not only these two guys are solutions to this recurrence relation, any linear combination of them is a solution. So take any constants, alpha 1, alpha 2, and combine these two solutions in a linear way like this. That function also satisfies this recurrence relation. And indeed, it satisfies them for any constants alpha 1, alpha 2. So you can make alpha 1, 1 and alpha 2, 0, in which case you're going to get this solution. Or flipping this will get you this solution. But any linear combination of these two is also a solution to the recurrence relation. That solution is called general solution. Every solution to this recurrence relation has to have this form. And which constants alpha 1 and alpha 2 you should take, that depends on the base conditions. So let's see first that that this is indeed a general solution. So I claim that if I have a recurrence relation like this.
Hey, Professor, I don't mean to interrupt, but the screen right now looks very, very blurry. We can't read anything.
Yeah. Okay, good. Thanks. Minus 6f and minus 2. It's better, right? Okay.
Yes, it's better.
So and I claim that so this is the recurrence relation, and I claim every fn equals alpha 1 2 to the n plus alpha 2 3 to the n satisfies this recurrence relation for any alpha 1 alpha 2. So it doesn't matter what these constants are, it always works. Okay, you can prove that by induction. But we'll just do the inductive step. So assume, let's look at what Fn is if this claim holds, and I guess it's a strong induction, because we'll assume that it holds for, assume it holds up to n minus 1. Okay, that this formula is correct. So let's see if it holds for n. So Fn is, I'm using the recurrence relation, right? So this is by this. And now if the assumption holds about these guys, that they are indeed expressed using this formula, then I can rewrite this as alpha 1 n minus 2, right? Because I'm using this formula at index n minus 1, plus alpha 2, 3 n minus 1, right? This is by inductive assumption. hypothesis applied to this term. And this is minus 6f and minus 2. But by inductive assumption, this formula held for it. So what is it? It's alpha 1, 2 to the n minus second plus alpha 2 times 3 to the n minus second as well. So this is by the inductive hypothesis. Right? I can assume that. Okay, so the rest is algebra. Let's take out alpha 1 term common, and what do we get? 5 times 2n minus 1 minus 6 times 2n minus 2, right? I gathered these terms. And now I'm taking out the alpha 2 terms, and what I get, 5 times 3 to n minus first minus 6 times 3 to n minus second. Okay, and now this thing is what? It's 5 times 2 minus 6 times 2 to the n minus 2, right? Because I just take 1, 2 out of here, and I get the 2 to the n minus second as a common term, and I have to multiply that 2 by 5. And I do the same here. I take one of the 3's out, and I just isolate the common term 3 to the n minus 2. And this is 10 minus 6, which is 4, which is 2 to the 2. And this is 15 minus 6, which is 9, which is 3 to the 2. So this is alpha 1, 2 to the 2 times 2 to the n minus 2 is 2 to the n. And the same with the 3's, right? 3 to the 2, 3 to the n minus 2 multiplied give me 3 to the n. Okay, so it's going to work. Does not matter what those constants alpha 1, alpha 2 are. If and from this also you can see why the roots, these bases, have to satisfy the characteristic equation. But I'm not. But this is, you know, enough for general stuff. So let's go back to the slides. Okay, so it is always a linear combination of these terms is a general solution. It always works. Okay, and now how do you find these constants? Okay, so you find them. Oh, okay. Do we have time? Yeah, sure. So let's try to do this for some other recurrence relation. Okay, so you have a recurrence relation. Somebody is asking, please answer Sebastian. You know, there's some answer on the chat to try to answer him, somebody. Okay. So okay, how do we do this? How do you solve this recurrence relation? So this might be a little too much to try to do this in your head. Let's do this all together on a piece of paper. So Fn is 4 times Fn minus 1 plus 5 times Fn minus 2. I will stop sharing so that people on the YouTube has a better view, right? I mean, the other stuff was not that important. So again, okay, so you know, educated guess, basically knowing this method means that you know that every solution has this exponential form. So plug it in. That's xn is 4x to the n minus first plus 5 times x to the minus second. Then you divide by x to the minus 2, right? you're left with all these powers vanish. X n minus 1. So look, x n minus 1 divided by x n minus 2, that's the same as x n minus 1 times x2 minus n minus 2, right? Because dividing works like this. And this is x2 n minus 1 minus n minus 2. And this is x2 n minus n cancel, minus 1 plus 2. Okay, so this is this guy is going to give me x to the 2, because by the same token, x divided by x to the n, x to the n divided by x minus, yeah, is xn minus n minus 2, and this is x squared. Okay, so this is the characteristic equation. And well, actually, the form of characteristic equation. Sorry. Yeah, no, I don't call that characteristic equation. I want it in this form. Okay, now this is the characteristic equation. I know it's the same thing, but we like it in this form because it's okay. It's just conceptually. I mean, okay, it's the same thing, obviously. So, what are the roots? The roots have to add up to -4, and I mean add up to 4 and multiply to 5. So what is it? Okay, if I have a minus here, so this means that there's one of them must be with the minus sign and the other with a plus sign. So if they multiply to 5, so it's 5 and 1 or 1 and 5, right? But they add to -4, so now I know that this is -5 and this is +1, right? Because this way I get -5x plus x, so -4x. -5 times 1 is, right? So the roots are x equal 5 and x equal -1. And you can check 25 minus 20 minus 5 is 0. -1 squared, which is 1, minus 4 times minus x minus 1, that's +4, minus 5 is 0. Yeah. So what is the general equation? It's some constant times the first root to the nth plus some other constant times another root, the second root to the n, but I have to take this in a bracket because it's negative, right? So otherwise, right, if I wrote this, that's a stupid thing to say because that's -1 always, right? But yeah, that's a very different thing from -2 to the n, right? Okay, so this is the general solution. Okay, and now we are back. Any questions to this one? How I get there? Okay, let me go back to the slides again. Okay, so it's this one. Okay. Oh, on my sheet I switched alpha 1 and alpha 2, but that doesn't matter, right? Because it's this is a solution for any constants. So how you order those constants is up to you. In fact, how do you even name these constants is up to you. You can call them A and B, C and D, or whatever you want. And there is no notion of first and second root, so you can order them any way you want to. By the way, I didn't quite tell you what happens when I chose my examples in such a way that the recurrence relation I have leads to a quadratic equation that happens to have two roots which are distinct. That's not always the case, right? There is quadratic equations that don't have any roots in reals, or they have a single root, right? Like, for example, x squared equals 0 has a single root, right? Like, so I basically didn't tell you how to solve these, and it is in the book as well, generalizing to that case. But I will not be asking you how to solve this on the test. So okay, so now let's go back to how to fit these constants alpha 1, alpha 2 to the initial conditions. So let's go back to the first example we had of a recurrence relation, which was this one. This was its characteristic equation, and it had two roots, 2 and 3, and therefore the general solution looked like that always. And now we have to find these constants, and they depend on the base cases. So look, this recurrence relation, how many base cases do you need in order for this recurrence relation to define a sequence? You need 2, right? Because nth guy is defined in terms of previous 2. So you need 2 at every step, right? You always need previous 2. So in order to hook this up, somehow you have to define what the sequence its values are on any two points, subsequent points, right? So let's say you started from from index 0, so you define f0 and f1. They must be defined as base cases, and indeed that is enough to find the closed form formula, because these base cases give you 2 conditions on what alpha 1 and alpha 2 have to be. If this is a formula for all n, then in particular it has to work at index 0 and index 1, which is your base points. So let's see how this formula resolves if I take n equals 0, where it's alpha 1 times 2 to the 0 plus alpha 2 times 3 to the 0. But these are just 1. So f0 simply have to be a sum of these constants, alpha 1 plus alpha 2. In n equal 1 case, you are using this general formula instantiated with n equal 1. So you get this, alpha 1 times 2 plus alpha 2 times 3. That has to be equal to the first element, the f1 element. So this gives you a system of 2 linear equations that you can solve for alpha 1, alpha 2, because f0 and f1 are given to you. These are defined as base cases of the sequence. Like, for example, for Fibonacci, f0 is 1, f1 is 1. And now you can solve for alpha 1 and alpha 2, right? Because you have the system of 2 linear equations. So that also sort of should give you like a kind of intellectual, I don't know, sense of relief, right? That you see that indeed, in order for this general solution to define a particular solution, I need 2 constraints that would allow me to define what alpha 1 and alpha 2 are. The initial cases, therefore, need to be 2 initial cases to define these 2 constraints. and this suffices. So given the general formula and given the initial constraints, this defines these, right, uniquely, because well, not every system of linear equations has a solution, but this is a very special system of linear equations where the coefficients for alpha 1 and alpha 2 are of this form. They are powers of some basis. This type of system of linear equations will always have a solution. Okay. It has a name. I think it's Hadamard, but I hope I'm not messing that one up. These type of system of linear equations. Okay. So this is the blueprint. You have a recurrence relation that is linear and homogeneous. You plug in fn equal to x to the n to get to the characteristic equation. If it's a degree g relation, recurrence relation, the characteristic equation will be degree g. You're solving for the roots, and if we cook up a correct example for you, then these roots will be unique, and there will be g of them. And based on these roots, you will set up a general solution, right, which is as on the previous slide. Some constant times the first root to the n plus constant times second root to the n, etc. And then you will use initial solutions, initial conditions, to set up a system of d linear equations, because if there's a recurrence relation of degree d, so it needs previous d terms, you have to start with d base cases, and then you solve that for the for those constants, alpha 1, alpha 2, or to alpha d. Okay, so, and that's it. And then you plug in the constants and into the general solution, and that's called a particular solution. And that's the solution to your equation. Well, we can try to you know, go over an example where what was our okay, so our equation was fn was 5 fn minus 1 plus minus 6 fn minus 2, and we knew that fn has to have the general form like this. Okay, and now we, okay, so let's say that okay, so this is a general solution, and I'm skipping the, you know, intermediate steps of characteristic equation.
Professor, you're out of focus again.
Oh, okay. Okay, better?
No.
No. Come on. Okay.
That looks good.
Okay, great. Thank you. Okay, so let's now let's say that f0 is 1 and f1 is 2. Okay, let's see what this does. I actually don't know what this would do. So it follows that that f0, if f0 is of this form, so it's alpha 2 to the 0 plus alpha 2 3 to the 0, that is simply alpha 1 plus alpha 2, and we know that this has to hit this base case. And f1, which is alpha 1 2 to the 1 plus alpha 2 3 to the 1, which is simply 2 alpha 1 plus 3 alpha 2, this has to hit 2. Okay, so now let's solve this system of linear equations, right? linear equation system. Okay, so how about subtracting 2 of these from here, right? So so I get so I have minus 2 alpha 1 minus 2 alpha 2 is equal to minus 2, and 2 alpha 1 plus 3 alpha 2 equals to 2. I just took this guy and multiplied it by minus 2. Okay, and I summed them up, right? So this guy vanishes. This is alpha 2, and alpha 2 is 0. No, sorry, it's not. It's yes, right? Because alpha 1 got cancelled, and what do I get? 3 alpha 2s minus 2 alpha 2, and then 0. Okay, so what is alpha 1 therefore has to be 1. Okay, I guess I could have guessed that, and it does work, right? Like alpha 1, the sum of these guys is 1, and 2 times this guy plus 3 times this guy is 2. So the particular solution is Fn equal to, so my constant alpha 1 was 1, so it is 2 to the n, and my alpha 2 was 0, so this time vanishes. So that's it. Okay, so these base cases result in this formula. Let's okay, you know what? Let's try to let's say F01, F13. What do you think that will get? It basically has to get this. Yes, because I just computed this formula for n equals 0, got me this, and n equal 1 got me here. So that has to work. But let's see that it does. Okay. So how do we do this? Okay. So F0 is alpha 1 plus alpha 2, so that's 1. Yes. And F1 is, I know that this is 2 alpha 1 plus 3 alpha 2. I don't have to repeat this stuff. And now I know this is 3. So I do the same elimination, right? Or just use that alpha 2 is 1 minus alpha 1. Yeah, okay, and stick it in there and see what happens. So 2 alpha 1 plus 3 1 minus alpha 1 is equal to 3. Well, this side is equal to this side is equal to minus alpha 1 and plus 3, and this is equal to 3. So therefore alpha 1 is 0, and therefore alpha 2, which is 1 minus alpha 1, is 1. And indeed, if I stick them here, right, I get Fn, which is 0 times 2 to the n plus 1 times 3 to the n is this thing. Okay.
Hold
so
on, I got alpha 1 equals 1 and alpha 2 equals 0. I think that's the opposite of what you got. Or am I looking at a previous problem?
I don't know. Sorry. I don't know. I mean, I'm getting what I should be getting, which is this, because I just picked up this initial conditions based on this being the. So I knew what particular solution I wanted, so I created initial conditions so that to fit this, and using this computation, I see that the only alpha 1 and alpha 2 that solve this, I mean, you can see this here. The only alpha 1 and alpha 2 that can solve this, right? I mean, the solution is alpha 1 is 0, alpha 2 is 1. Yes, and it works. The sum of these two guys is 1, and 2 times 0 plus 3 times 1 is 3. This is easy to check that these solve this system. Okay, and therefore, this is the particular solution, which is this. There is many ways to solve a linear system of linear equations. So we are not teaching you how to solve system of linear equations, right? There's many ways. You can take these and multiply them by something and add the rows. You can do substitution like this and stick it in here. All these methods are equivalent, and each of them gets you a solution. The important thing is that once you get the solution, it's kind of easy to verify it, right? You just check that each of these equations is correct. Yes. So no matter what method you used, you can always verify your solution. And if there is a mistake, you just have to recheck your math. And this solution gives you a particular thing, right? And if we modify these base cases to anything else, basically, right, then you're getting some combination of these two functions. So some, we got special cases where either alpha 1 or alpha 2 was 0, and modifying these base cases is going to give you where particular solutions where alpha 1 and alpha 2 are, none of them is 0. Okay, so go to of course the textbook guides you over this methodology as well, and then there are multiple exercises. I will keep some of them open so you can verify test yourself on them, and then I think some of them are in the well. I now put some of them in the next homework. Okay, so thanks so much. Somebody says use a calculator. I none of the examples that I will give you will require using a calculator.